Okay, welcome back to Unit 8, Stoichiometry. And in this recording, we will be doing mass-to-mass type of conversions, and then we'll talk about percent yield and limiting reagent type of problems. So our flowchart will help us with these as well. It's the same one that we used in the previous slides. And in this one, we will be going from grams to moles, moles to moles, and moles back to grams. And of course that will be a three-step conversion type of problem. Okay, so first we have to have a balanced equation, and in this equation we have potassium, which is +1, a phosphate, which is -3, a calcium, which is +2, and a hydroxide ion, which is -1. So calcium is going to combine with phosphate, and then we have hydrogen reacting with hydroxide. HOH, the same thing as good old high quality H2O. So now we will put the charges back over the top, crisscross the charges if they are different from each other, and then we will balance the equation. So here we go, we'll balance from left to right and do the arrow sign, and then we'll go back and double check. So we have 3 hydrogens there, so we'll need a 3 on the product side, 1 phosphate and 2 phosphates on the product side, so we'll put a 2 next to our phosphate. Now it'd be tempting to go back and try to adjust hydrogen, but we need to go all the way through first one time and then go back and double check. So we have 1 calcium on the reactant side, we have 3 on the product side, so we'll need to put a 3 there. 3 times 2 is 6 hydroxides, so we'll have to change this coefficient to a 6. So let's double check. 2 times 3 is 6, 6 hydrogens. 2 times 1 is 2 phosphates, 2 phosphates, 3 calciums, and 3 times 2 is 6 hydroxides and 6 hydroxides. So now we are balanced. This particular problem says how many grams of water can be produced when 75 grams of phosphoric acid reacts with excess calcium hydroxide. All right, so we are solving for water here, grams of water, and we are given 75.8 grams of phosphoric acid. So we're given 75.8 grams here, and we are going to go to grams of water. So grams to grams type of problem. As always, we'll write down our given, which is 75 grams of phosphoric acid, H3PO4. So we're going from grams to moles, moles to moles, and moles back to grams. So 3 different steps here. So we'll have 3 conversions, grams to moles. Whenever we have grams and moles together, it'll be 1 mole, then moles to moles, and then moles back to grams. Moles here, I'm color coding it. 1 mole is equal to so many grams of H2O. And then we have moles on the bottom here, moles of H3PO4. All right, this is H3PO4. Okay, so a 3-step conversion. And so now we just got to fill in our values. The first one is grams of H3PO4 per moles of the same. So whenever you go from grams to moles, you need the molar mass off the periodic table. Have 3 moles of hydrogen, 1 mole of phosphorus, and 4 moles of oxygen. 16, 31, and 1. 6 times 4 is 24, be 64 there. 4, 5, 6, 7, 8, be 98 grams per mole. 98 grams per mole. All right, so now if we were to leave it there, we would just have moles of H3PO4, but we've got to change from moles to moles right here in our next step. So how many moles of H3PO4 according to the balanced equation? Well, there's 2 moles of that guy. And how many moles of water? We have 6 moles of water. 6 moles of water. And for every 1 mole of water, we have so many grams. 2 times 1 will give us 2 grams of water. Oxygen, 1 times 16 will give us 16 grams. So we have 18 grams of good old high quality H2O. A lot of work there, but the steps aren't any more difficult than the other problems that we've done. So now we need to multiply across the top and divide by the bottom. So I get 41.3. So our answer here is 41.3 grams of water. Okay, so we have another problem coming up. Why don't you try to work that one and then pause the video and work that one, and then we'll come back and discuss it. Okay, hopefully you did that. So let's work this one. Why? Because it's so much fun. We have 156.8 grams of calcium phosphate, and this is grams of calcium hydroxide, so it's another 3-stepper because it's grams to grams. I won't try to color code this one. And so we have grams of calcium phosphate on the bottom. Whatever you start off with here has to go on the bottom so it'll cancel out per 1 mole of calcium phosphate. And we have moles of calcium phosphate on the bottom, and we are going to go to calcium hydroxide. So we'll need moles of calcium hydroxide on the top, and then we'll need moles of calcium hydroxide, 1 mole per grams of the same. Okay, yep, there we go. All right, so grams to moles, and moles back to grams. So we need to figure out the molar mass of calcium phosphate. So let's do that. Ca 3 moles of calcium, 2 moles of phosphorus, and how many moles of oxygen? 8 moles of oxygen times 16, 31, and 40.1. So that'd be 120.2. That'd be 62. 6 times 8 is 48. 8 times 1 is 8. 9, 10, 11, 12. 128. 2, 10, 11. 310.2 is what I got. You double check me and make sure. So now we're at moles of calcium phosphate. So how many moles of calcium phosphate are there? Well, if there's nothing there, it's understood to be 1. So for every 1 mole of calcium phosphate, how many moles of calcium hydroxide do we have? So let's find that guy, and we have 3 moles of calcium hydroxide. And so for every 1 mole of calcium hydroxide, how many grams do we have? Okay, so we'll have to do that one. So this one, calcium hydroxide, has just 1 mole of calcium, 40.1. Oxygen, we have 2 moles of oxygen times 16 will give us 32 grams. And then hydrogen, we have 2 times 1 will give us 2 grams there. Add all those up. 2 and 2 is 4, and 74.1 there. Okay, 74.1 grams. Getting a little sloppy there, but let's circle everything here. So we got 156.8, we've got 3, and then we got 74.1 on the top. 310, and 1 will not change anything. Just multiply anything by 1 and you get that number. So it'd be, I get 112.2, 2 grams of calcium hydroxide. Okay, so kind of a long process, not any harder than anything that we've done before. Just takes a little bit more time, a little bit more patience to work those problems. So the next one that we will work on the next slide is a percent yield type of problem, and we'll use the same flow chart that we did before. I wrote down the equation here to save us a little bit of time. And so on these types of problems, you'll work a grams to grams type of problem. That is, if you're given grams of a product, and then you will compare the actual yield in the laboratory and compare that to the theoretical yield that you calculated using stoichiometry. And in this particular problem, we're given 100 grams of hydrogen sulfide gas. And so let's write that above hydrogen sulfide here. And then you're given grams of water, but we will calculate that out using stoichiometry. The given grams here will be an actual yield. So that's the actual yield produced in the laboratory. So we'll do our stoichiometric problem, writing down our given, our grams of hydrogen sulfide gas here. And just like before, we'll go from grams to moles of another chemical, and then moles back to grams. In this case, our other chemical is going to be water. So grams of hydrogen sulfide will go on the bottom per 1 mole. So let's go ahead and do that. So hydrogen's 1 gram per mole, and we've got 2 of those. Sulfur is 32.1 grams per mole, which will give us 34.1 grams there. All right, and then now we'll have moles of H2S on the bottom, hydrogen sulfide, and moles of good old high quality H2O on top. And then for every 1 mole of H2O, I believe I remember that from the last slide or slides past, or 18 grams per mole. You forgive me if I don't calculate that out for you. So now all we've got to do is look at the molar ratios here. So for H2S, hydrogen sulfide, we have 2 moles of hydrogen sulfide gas, and we have 2 moles of water here in our balanced equation. So now all we have to do is multiply across the top and divide by the bottom. And I've already done that for us here, and I get 52.8 grams of water. Okay, so there's our theoretical yield. And so to get the percent yield, it's actual over theory times 100. So our actual yield is what's given is 33.2 grams over our theoretical yield, which is 52.8 grams times 100. And when we do that, we get 62.9%. If you're doing really good, you get somewhere in the 85 to 100% range. This one, not so great. Not so great a yield. I don't know if some of it evaporated or what, but any number of things can happen in the laboratory to cause you to have a lower yield than expected. Sometimes you get a slight conversion to energy, or in this case, you might have gotten some evaporation of water. The product could get caught up in maybe the filter paper, and you didn't get quite all of it scraped off, or maybe your weight of your filter paper, you didn't actually calculate that correctly. So there can be any number of things to go wrong. So the next slide, we are going to do something called limiting reagent problems, and I think you'll find those quite fascinating as well. Okay, so now we are going to do one of the granddaddy of them all type of problems, limiting reagent problems. And the flow chart remains the same, and we are going to use one technique to do that. You can do these problems a couple of different ways. We'll do my favorite, and then maybe in another set of slides, we may show you another technique to do the same type of problem. Both of them require about the same amount of work. So you are given 2 reactants. Let's say peanut butter and bread, all right, as our example. So let's say that we want to make sandwiches, and we are given 4 pieces of bread and a jar of peanut butter. Well, it doesn't take a genius to figure out that if you use 2 slices, 2 slices for each sandwich, you can only, if you have 4 slices of bread, you can only make 2 sandwiches, 1 and 2, right? And then you'll have a whole bunch of peanut butter left. Well, that's kind of how it is in chemical reactions. Sometimes when you have 2 reactants, one of the reactants runs out first, and we call that the limiting reagent. And then the other one, that the limiting reagent, the bread, determines how much sandwiches you can make, or how many sandwiches you can make. So the limiting reagent determines how much product that can be made. And we figured this out by doing the problem in two different steps. We figure out the limiting reagent, and then from there we can figure out how much product that we can produce. And then in a separate step, we can figure out how much of the peanut butter is left, or the excess reagent is left. So let's do an example problem here. So we are given, I went ahead and balanced the equation. So we're given here 110.5 grams of hexane, that's this guy right here, and we're given 110 grams of oxygen. So pause the video and write down the problem, and then we'll work it together. Okay, hopefully you've done that. So let's do the problem. We'll start off with 110.5 grams of C6H14. Okay, and so we're going to go change that to moles of our product that we're asked to solve for, which is water. So we're going to solve for water here. It'll be grams of water. But we're going to turn it into moles first, and then we're going to compare the moles of water that can be produced from the hexane and the moles of water that can be produced from the oxygen. And so we'll work these side by side. So we're given 110.0 grams of oxygen, and we are going to turn that into moles of water. So we have grams per 1 mole of hexane, and I looked that up already. Is 86 grams per 1 mole of hexane. And oxygen, we have for every 1 mole of oxygen, we have 32 grams. So this is C6H14 here. Okay. And then finally, let's do the moles to moles. So C6H14, there's 2 moles of C6H14 per every 14 moles of water. And so oxygen, we have a whole bunch of oxygens there, moles. We have 19 moles of oxygen per every 14 moles of water. Okay, so now we're going to work these just like any other stoichiometric problem that you go from grams to moles. We'll multiply 110.5 times 14, right, and divide that by 86 times 2. And here we get 8.99 moles of water. And here on the bottom it's 110 times 14 all over 32 times 19. We can already tell that that's going to be a smaller amount. And there we get 2.53 moles. So now the one that produces the fewest number of moles of oxygen is going to run out first, and it's going to be the limiting reagent. So here our oxygen is our limiting reagent. So that's going to determine how much water can be produced. And so we'll just go ahead and figure that out here. So for every 1 mole of water, you have 18 grams. So our final answer here is 45.6 grams. So in this particular case, our oxygen is our bread. It's going to run out first, and then we're going to have some hexane left over at the end of the reaction. So how you figure out how much of the excess remains is you start off with where the reaction ended at 2.53 moles of H2O. And to give ourselves a little bit more room, let's work that on the next slide. Okay, so we have 2.53 moles of H2O at the end of the reaction. And so the question is, how many grams of the hexane were used? That's the excess reaction, or the excess reagent. So here we go from moles of water to moles of hexane. And if we look on the balance equation, we had 2 moles of hexane per every 14 moles of water. And then for every 1 mole of hexane, we had 86 grams of the same. 6 times 12 gives you a number, then plus 14, right? will give you 86 grams. And then when we work that out, 2.53 times 2 times 86 divided by 14, I get 31.1 grams of hexane used. Okay, and so to get what's left, you would take the 110.5, that's the original amount that we started with, minus 31.1 grams used, and we get 79.4 grams of C6H14 that is left. A lot of steps there, and it takes lots of practice to do these. There's several practice problems like this in your set with solutions for you. So work those out and see how you come. So this concludes Unit 8, Stoichiometry. In Unit 9, we will be talking about gas laws, and those are really, really fun to do as well. And now you have lots of skills on making chemical calculations to help you with the concepts in the gas law chapter. So looking forward to seeing you then. We'll be doing more calculations, learning more chemical concepts and the relationships between all these wonderful phenomena such as chemical reactions and gases and all things chemistry. So looking forward to seeing you then. Peace.